It's Mr. Spudik again. Today we're going to talk about Isaac Newton and his 3 laws of motion. So, before Isaac Newton, there were a lot of people that said they were scientists. There are a lot of people that have different theories. And when they saw things around that seemed to make sense, they figured it must be science. They must know what's going on. Sir Isaac Newton is going to print the Principia, which is going to be the most important book for our physics class. And really, as we know physics in this class, Sir Isaac Newton is really the Mac Daddy. He's the grandfather of it all. He's going to be the one that will teach most of the things we learn in this physics class. Okay, so like I said, the book he wrote was called the Principia, or the Principia. And it had 3 very important laws of motion. The first law of motion, okay, is the law of inertia. And what it says is that an object will not change its velocity until an outside force acts on it. Now, you might think that's not a very interesting or exciting law. You might think, that's kind of common sense. But at the day, and honestly, when you start thinking about other things you've seen around you, it's a little bit more groundbreaking than you think. Okay? Before Sir Isaac Newton, let's give it a scenario. Okay? Before Sir Isaac Newton, let's say you threw a ball. Okay? And you threw this ball as fast as you can and as hard as you can into the air. Well, what would happen to that ball? The ball would travel through the air until it fell down, hit the ground. It would roll and then finally stop. The scientist, the person that would be considered maybe the physicist before Sir Isaac Newton, was Aristotle. And Aristotle would say that this tennis ball stopped because it's supposed to. All the objects here on Earth are not supposed to move, so if they start moving, they will eventually stop. All the objects up in the sky are supposed to keep moving, and that's why they still move. Okay? So that sounds crazy to you and me, but if you think about objects and you just see something stop, you might kind of say, well, I guess it was kind of supposed to stop. So what Isaac Newton says is this. Using this example, if I throw this tennis ball, it goes in the air. I throw it in a straight line with a certain velocity. Soon, gravity, or actually the instant I let go of it, gravity is going to start acting on it. So you have an outside force that's going to act on this ball and change its velocity and pull the ball into the ground. Once it's in the ground, it might still be moving, but other forces like friction, the friction of the grass, the dirt, whatever's hitting it, will slow that ball to a stop where it finally is going to sit still. Okay? So that is Isaac Newton explaining why this ball would stop. Okay, so the law of inertia says not just for things moving that they're going to stop because of outside forces, but also something that's sitting still will want to sit still until an outside force acts on it. Okay, so if we take the scenario of the ball and we go and talk about going out into outer space, okay, where there's no other forces, any other forces to act on it, and I take this ball and I throw this ball as fast as I can into space, that ball will have the same velocity in the same direction forever. Or if some outside force can act on it. But if I can throw it out into space and no other forces, no other gravities or anything else act on it, this ball will go with the same velocity in the same direction forever. And that's the law of inertia. Okay? All right. Again, you can say that unless an outside force acts on it, that object will have the same velocity forever. Now, there are examples that you can look at later on. And I have the example of, say, a baseball player. Sometimes you'll see a baseball player, very rarely, but there are certain baseball players that have been able to a check swing, meaning they started their swing and then they held back and they hold back the handle. However, the top of the bat keeps going and they break their bat on a check swing. Okay? And the reason that can happen is the top of the bat still had so much inertia to it that the bat wanted to keep traveling forward even though the handle stayed, and the bat's going to break. All right? Also, you know, I'm an awesome golfer, so this wouldn't happen to me, but I had a friend one time that would keep missing the tee or keep missing the ball, and when he would hit the tee, the ball would still sit there because he was going right under the ball and hitting the tee. Okay? You've also maybe seen the example with the dishes on a table where you have somebody hold on and there's dishes on a table, but they grab by the tablecloth and they will yank down that tablecloth as fast as it can go, and the dishes will stay on the table sitting still. Okay? For all of these are all examples of inertia. Okay? The bat had the inertia keeping going forward, so it kept moving forward even though it broke in half. Okay? The golf ball was sitting still, and because my friend hit the tee, the golf ball still stayed in that same spot. And the dishes had inertia. They were sitting still, and even though somebody yanked the tablecloth from underneath, the dishes stayed in the same spot. All right, now let's talk about Newton's second law. For Newton's second law, we want to talk about acceleration. And what Sir Isaac Newton noticed was this. If you applied a force to an object, some people think that when you apply a force, it makes it go. Okay? But it's not that it just makes it go. It doesn't just affect its velocity. The more force you apply, the more acceleration you'll get. Okay? So the more force you can apply to something, the more acceleration you will get. The more it will accelerate. So if you push something along, okay, it'll have a greater net acceleration. Now there is friction and all that stuff fighting against it, so there's going to be other things fighting against you. But if you apply and you have some kind of net force, taking away what friction does, the more net force you apply, the more it's going to accelerate. Okay, and that's direct proportionality. So if you think of it as, in math terms, that would be direct proportionality. And we'll talk about math terms and writing kind of an equation in a minute. Okay, the second thing he noticed was this. When Sir Isaac, if you were going to apply a force, okay, the same amount of force to get something to accelerate, but the mass increased. So you were accelerating, pushing along something that had one set mass, and then all of a sudden, you had to get more mass to accelerate. The more mass you had, the less acceleration you'd have. So there's an indirect proportionality between mass and acceleration. More mass with a set amount of force, less acceleration. Okay? So we want to kind of tie these two things together. We have force, we have mass, and we have acceleration. All right? So you could think of it as acceleration is going to be directly proportional to force and indirectly proportional to mass. You do a little bit of algebra and you'll get Newton's second law, which is the equation that net force equals mass times acceleration. F equals ma. Now, why do we say net? Okay, like I said before, you could have other forces fighting against it. So think about your paycheck, right? Your paycheck, if you work so many hours at a certain pay rate, you could multiply those two things to get your gross pay. But that's not what you end up getting, right? You'll have taxes taken out. So the net pay is what you actually take home. Well, it's the same thing with forces. You could have one force. If I push something, that would be like the force I give it. That's my gross pay. All right? But other forces can fight against it. And if I have friction fighting against me, it's like a tax, it's going to take away some of that force. But after all said and done, whatever the force is that causes the object to accelerate, that is the net force. And the net force is equal to mass times acceleration. All right. Now, Sir Isaac Newton's third law is the law of equal and opposite forces. And what it says is this. For every force, there will be an equal and opposite reactive force fighting in the opposite direction. If I'm going to apply a force to this tennis ball, there has to be an equal and opposite force fighting against me in the opposite direction. Always. Always, always, always. Now, this can get confusing. Okay, for some students, you can think about it, and there's some questions people ask. Well, how do you move? Okay, how can that happen if there's always an equal opposite force? The key is to look at the surface. Okay, the key is to look at the surface where a force is being applied. Right here, okay? If my hand is applying a force to that ball, there has to be a force from the ball being pushed back on my hand. Always. Okay? What if I'm pushing someone and that person is lighter than me? Well, you would say, well, who's applying a greater force? If I push on somebody and I'm trying to push that person away, if that person is lighter than me, shouldn't you say, well, I must be applying a greater force? But that's not true. If you look at the surface where my hand is pushing the other person, the forces are equal. Well, why does that person move and I sit still? Well, the forces are equal, but I might have a bigger mass. Okay? I might have more friction in my shoes. So there might be a lot of reasons why I don't accelerate backward as much. But if you just look at the surface, there will always be equal and opposite forces. Okay, let's think back to the whole thing about space again. All right, let's say that I'm going to throw something in outer space. I have a hammer, and I'm in outer space, and I throw the hammer in one direction. Okay, the force I apply on the hammer will be equal to the force being applied from the hammer back to my hand. The hammer is going to go really far, and it's going to have a high acceleration. But I am going to accelerate too. I don't have any friction holding me back. I will have an acceleration going the opposite direction. Will I have the same acceleration as the hammer? No, because my mass is smaller. Well, I'm sorry, my mass is bigger. My acceleration is smaller. But mass times acceleration on the hammer will be equal to mass times acceleration on me. Okay? And so you can see other examples out there. There was a movie, a Disney movie called WALL-E. And there's a good little scene where WALL-E's in outer space and he has a fire extinguisher. And it was the same idea. He pushes on the fire extinguisher and the gas is going to get accelerated out really, really fast in one direction, but he's going to accelerate as well. Okay? He has a bigger mass, he'll have a smaller acceleration. If the gas has a smaller mass, will have a greater acceleration, but still the forces are equal. MA equals MA. Thanks for watching today, and I'll see you later.